Hi guys. If you're new here, this is Lightspeed, a space exploration game centered around time dilation. And to begin exploring space, the first thing we need is a homeworld, which, at the end of the last video, looked like this. When viewed from above, it's lit so evenly and appears so flat that it's impossible to tell where any of the hills and valleys are. On top of that, there's many places where the ground collision doesn't even match up with the visuals, and if I ever wanted to land a spaceship, it would be beneficial to know exactly where the ground is. So to kill two birds with one stone, I decided to completely redo the way I make the planet. You see, a big part of the issue was the initial decision to build the planet in a regular Godot shader. Shaders are special programs that run on the GPU, and they tell the computer how to display your game. I used shaders to move the points on a sphere and change their color to create the terrain. And two big problems arise with this. The first is that after moving the landscape up or down, the normals are not recalculated in the shader. So what does that mean? The surface normal can be thought of as the direction that points directly away from the surface at any location. For example, if you start with flat ground, all of the surface normals will be pointed straight up. But if we introduce hills, we should see the normals change to point more outward, away from the slope of the ground. Since this recalculation isn't happening, what we have is hilly terrain where the game acts like every spot on the ground is still pointed straight up. And these normals are what defines the direction that light reflects. The end result is this. Even though you can still see along the edge that there are hills and valleys, the light acts as if the whole planet were still a perfectly smooth sphere. But even if we could solve that, I mentioned that there were two problems. The second is that the shader runs on the GPU right before the frame is output to the screen. This makes them very fast, but there's no point at which the data makes its way back to the CPU. So when we create the terrain in the shader, we can't use any of that terrain information in our game scripts. And moving the terrain up or down in the shader only affects how it's going to be displayed on the screen visually. It doesn't actually move any of the geometry of the planet, meaning that the ground the player stands on is still just a smooth sphere. To work around this, I ended up generating the ground collider from the same height map as used in the shader. This meant that I was now doing the work to build the terrain twice, once in the shader and once in the game code. This basically negated the advantage of using the shader in the first place. And to make matters worse, the two didn't even exactly line up, leading to the player clipping through the ground in some areas. What I needed was a single location to generate the terrain, both visually and for collisions, and ideally continue leveraging the enormous performance advantage that comes from running on the GPU. The solution was compute shaders. A compute shader is a special type of shader that runs on the GPU, but instead of outputting graphics to the screen, it runs computations that can be shared with the CPU. This was not exactly the most straightforward process. Even passing arguments to and from the shader is not obvious. For example, within the GD script used by Godot, if I want to pass an argument to a function, I call the function and supply the name of the argument. The function is defined to expect an argument of the type being supplied, and the return value specified by the function can be collected into a variable of the matching type. When passing arguments to a compute shader, I have to specify the number of bytes of memory I'll need to set up the shared memory buffer between the script and the shader. The size has to be a multiple of 16 to conform to Vulkan's API memory alignment specifications, and the input data should be transformed into a byte array before being passed to ensure the size matches the expectations. The data has to be padded with zeros to fill in the required space for the alignment, and the variables accepting the input data in the shader have to match the order and the alignment of the incoming bytes. To set up a compute shader, the boilerplate alone requires more code than most other script files in Godot, and while the documentation is good, examples and tutorials to do something like this are pretty sparse. The first step was to get the simplest working example and make sure I had everything set up right. That is, passing in an image and retrieving it completely unchanged. With that working, I know that at the very least my data is being passed correctly, so I could move on to constructing a planet. When setting up a compute shader, you're required to define the size of your work groups in 3 dimensions, X, Y, and Z. That's Z in freedom. At a very high level, these are groups that get dispatched together on the GPU, but we don't really need to worry about that. What's more useful for the purpose of building a planet is that inside the shader, you have access to an ID, which holds the current shader execution X, Y, and Z. So for coding purposes, these can be rationalized as 3-dimensional loop iterations. Since our planet is a cube sphere, it's very useful to define x and y to be the number of vertices along the length and width of each face of the cube sphere, and to define z to be the number of faces, 6. This way, within the shader, we can determine which face we're currently on, and where we are on that face. Then, sample the height map at the corresponding location, and move the vertex toward or away from the center of the sphere. If anyone would find this useful, I might make this code available, since it really is a crime that there isn't more information floating around about how to do this. And this is the planet we're able to generate. Since the terrain created by the shader is already available to the game script, unlike the planet we started out with, it's as easy as using the same data for the collisions. And just like that, we have ground we can walk on that matches the terrain exactly. It does look a bit Minecraft though. My initial thought was that this was due to a discrepancy between the height map resolution and the number of samples I was taking to make the terrain. I figured that if the number of samples were too high, it would sample from the same vertex multiple times before moving on to the next, leading to flat areas followed by a sudden jump. I added some code to sample from the neighboring pixels to try to smooth this out, which resulted in this bug that I found pretty entertaining. It makes me think of that frozen world from Interstellar. But moving along, it turns out that the reason for the blocky terrain wasn't due to an abrupt move from one pixel to the next, but an abrupt move from one color to the next. This is my height map. I never wanted to have extremely low lows or high highs, so I reduced the color variation, eliminating the darkest and the lightest values. And since this is only 8-bit color, there were only 256 distinct color values even before filtering them down. That means there simply weren't that many different values for heights, leading to these sharp transitions. So just for the time being, I switched my height map out with some random noise containing the full color range. And this is what I got. This already looks leaps and bounds ahead of what I started out with, but there's still something off about the lighting. Chunky almost. Right now, the surface normals are being generated by the compute shader as well, by sampling the surrounding terrain to calculate the slope at each point. After many hours of trying to find a better solution for this, finally, frustrated, I was taking a much needed break when it hit me. Doesn't basically every 3D rendering program that exists just kind of handle the normals automatically? Like, in Blender, there's a hotkey to recalculate normals. Shouldn't Godot have something like that? Ta-da! And, of course, it did. And to get back to the planet's original shape, all I had to do was pass the full grayscale version of the height map into the shader, and then in the shader code itself, limit the land height and the ocean depth. And so, adding back in the color, and I think it looks great. I didn't even do anything special to the lighting here, but there's something about the color gradient in the water that makes it look like a fog or a glow. It's almost dreamlike. So anyways, that's all I've got for now. I think next time we might take a look at the sky. I know Outer Wilds and some other projects I've seen use a kind of realistic atmospheric scattering, but so far that's not the approach I've been using. I'm not sure what I'm going to go with in the end, but we might take a look at that. Like and subscribe if you like this video, leave a comment down below. I'd like to hear from you. But that's it for now. I'm out.